So good evening, everyone. Uh, it's a great pleasure for me to introduce our guest speaker, Dr. Hemant Kumar. So I will introduce you. Dr. Hemant obtained his BTech degree with honors in Electronics and Communication Engineering from Kurukshetra University and a PhD in Electrical Engineering from IIT Bombay. He received various awards for actively participating in various academic and other extracurricular activities such as social, cultural, sports, and organizational. He has been awarded gold medal by Haryana State Governor for securing the first position in BTech. He is the recipient of the Best TA Award for his excellent contribution to the course Radar Systems at IIT Bombay. Currently, he is working as an assistant professor at NIT Tiruchirappalli. His research interests include broadband antennas, microstrip antennas and arrays, passive microwave circuits, monopulse tracking, and microwave imaging. He is serving as one of the editors in IETE Journal of Research and also serving as a reviewer in a number of national and international journals, including IEEE Access, IET Microwave Antenna and Propagation, IETE Journal of Research, and many more. He is a senior member of IEEE, life member of IETE, ATMS, and Institution of Engineers India. He has published many research papers in various journals and conference proceedings of reputed national international conferences, and also filed one Indian copyright and one Indian patent. So today, the title of his talk is Broadband Monopulse Antenna. In this talk, he would be discussing the basic concept of monopulse tracking along with the concept of EMCP microstrip antenna arrays and monopulse comparator. So we welcome you, sir. Kindly now proceed for the session.
Good evening. Thank you, Dr. Rajesh, for introducing me to the audience. So I'll just share my presentation. Please just let me know whether my screen is visible or not. So
Yes.
So I think I shared the presentation. Can you see?
Yes, your screen is
Oh,
visible.
okay. So I'll just make it full screen so that it will be
Yes.
visible.
Yes, now it is
Yeah.
perfect.
Okay. Good evening, all. So I will be starting my presentation, and the title of my presentation is Broadband Monopulse Antenna. So in this presentation, I will be introducing you the concept behind the monopulse tracking, the principle behind this monopulse tracking, how it works, and then I will be introducing the broadband microstrip antenna arrays, the monopulse comparator, and followed by the integration of the antenna and the comparator, which will tell us, which will give us a monopulse microstrip antenna. Right. So before introducing the monopulse tracking, I would just discussing a few techniques which can be used for tracking a target. So basically it is just a radar. So there are various techniques available for tracking a target. The first one is we can see a lobe switching technique, or also known as a sequential lobing. In this lobe switching technique, what happens, basically radar is just sends a signal and receive a echo from the target. Target reflects a signal towards the radar, and radar, based on the received signal echo, radar will determine the distance. Basically, if you see the radar, full form is radio detection and ranging. From the name itself, it says that it will be able to find out the you can say the detection and the range of the target. But nowadays radar won't only give you the range, it can tell you more information, like it can tell you the velocity of the target if the target is moving, and many other things it can tells, right? So initially it was just radar was developed just to calculate the range, or you can say the detection of only the target, right? So that's why the radar name was given. But later on, it was developed, and so many things we can actually determine the angular position, angular velocity, linear velocity of the target. We can easily determine using the radar. Right. So in this we have the first technique, the lobe switching technique. In the lobe switching technique, what happens? Suppose this is our target. This is our target. Just a second, my pen is not working. Yeah, this is our target is there, and this is our radar. So radar in the lobe switching, what will happen? It will send a beam or two beams. And if we want to track the target in one axis, in the horizontal axis, so what will do? This radar will send one beam in this direction, beam A, and after some time it will send another beam in this direction, and it will receive some echo, and the echo will be we can see the what is the amplitude for beam A and what is the amplitude for beam B. If target is right at the center, what will happen? Beam A and beam B will receive the same amount of echo. Both will receive the same amount of echo. So based on the difference between these two echoes, we can say the target is right at the center. We can take the case the target is off center. If target is off center in the direction of beam B, what will happen? It will receive more echo when we transmit beam B, and it will receive less echo when we transmit beam A in the direction of beam A, right? So in that case, we can say the difference is more towards the beam B. So we can say the target is along the direction of beam B. So this is actually a lobe switching, which can be used to track the target in both the axes. For if we want to track the target in one axis, we have to use two beams. And if we want to track the target in both horizontal and vertical, or basically we can say the elevation plane and the azimuthal plane. So in that case, we will need four beams. Beam A, beam B will be for one plane, and beam C and D will be for the another plane. So there will be two beams for the elevation plane and two beams for the azimuthal plane, right? So to track the target, we will require four beams, and this will be switched between one position to another position. So that's why it is actually known as lobe switching. Okay. The second technique is conical scanning. Conical scanning is basically a continuous version of this lobe switching. In lobe switching, what we do is basically the beam is switched between one position to the second position discretely. But in continuous conical scanning, it will continuously track around a particular axis. Around a particular rotation axis will be there, and the beam will be continuously tracking around this axis. And when the target is right at the you can say if the target is along the rotation axis, then the error will be zero. Like in this case, if the difference between beam A received echo and beam B received echo is equal to zero, then we can say the target is right at the center. If this difference is non-zero, then we can say the target is not right at the center. So we have to check whether it is towards beam B or towards beam A. So once the difference is zero, we can say target is exactly at the center. In both these things, lobe switching or a conical scanning, the issue is we have to use multiple pulses for one pulse for beam A, one pulse for beam B, like that. So we have to use multiple pulses. So what happens, suppose you are tracking a target, and the time interval during which we are measuring, the measurement is done with either you can say a lobe switching or a conical scanning. And during that time, it may happen that target may change its cross section, radar cross section, target radar cross section may change, or there may be some fluctuations in the target cross section, right? So or it can be in the weather fluctuations may be there, some attenuation. Because of those amplitude fluctuations, we may get means the accuracy won't be that much good for these two you can say the techniques. Suppose I'm just taking an example. Suppose target is switching its position. Target is switching its position as per the beam switching. Suppose at time t1 the beam position is A, and at time t2 the beam position is B, this direction, and target is at time t1 in this direction, and time t2 the target is also switching with the same speed. Suppose target is also switching its position, and the switching frequency of the target is same as the switching frequency of our beam, then in that case what we will see that beam A and beam B will be the same echo, and we will receive the same amplitude for both the beams, and we will think that the target is right at the center. Though the target is not right at the center, the target is actually switching its position. Okay, the target is switching its position from A to B with the same frequency as of our beam switching frequency. So in that case, the accuracy of the target location, or you can say, will be very less, right? So in this case, because we are using a multiple pulses, the accuracy will be less. So what is the solution to this problem is the monopulse tracking. From the name itself, monopulse, only one pulse will be used for tracking the target. This technique is also known as simultaneous lobing. So in this case, we will only use one pulse. So the amplitude fluctuations will not be there. So it will be very accurate compared to the previous two techniques. So that's why we are going to focus in this session on the monopulse tracking scheme. Okay. So I'll just discuss the concept, how it works. So what is a monopulse tracking? Monopulse tracking is basically will be using four similar antennas. Here, this is the you can say the conventional block diagram of monopulse tracking. This is, you can say, a horn antenna. In this horn antenna, there are four similar horns are there. You can say here. We can name it as A, B, C, and D. If if the target is right at the center of all these antennas, suppose a target is right at the center, I am assuming, uh, in that case, a single pulse will be sent towards the target, and the received echo will be received by antenna A, antenna B, antenna C, and antenna D. All these antennas will receive the echo because target is right at the center. So the echo received by the antenna A, B, C, and D will be same. This green part represents the echo received by, just to means understand the concept, just to explain the concept, I have just denoted the received echo with this green area. So if the target is right at the center, all the antennas will receive the same amount of echo. And if we assume all these antennas are similar antennas means the gain of all these antennas are same. So what will happen if the gain is same? So the amount of received signal will be same for A, B, and C and D, right? So if we calculate the sum of A, B, C, D, then we can easily find out the value of the distance of the target from the radar. Basically, if you want to track any target in the space, we need three variables. We have to find out the three variables r, theta, and phi. R tells you the distance of the target or the range of the target, basically from the radar. Theta tells you the elevation angle, and phi tells you the azimuth angle. So we need three values, and for three values we need one is the sum will tell you the value of distance of the target. Okay, so we will calculate the sum of all the received echoes, which will tell us the distance of the target. And azimuth difference, or you can say the horizontal difference, A minus B and C minus D. The horizontal difference will tell us the value of phi. This will give us the value of phi. So if this value is non-zero, based on that non-zero value, we can easily calculate, we can just process that signal received non-zero value, and we can find out what will be the value of phi. If this azimuth difference is zero, in that case we can say phi is zero. Okay. Similarly, we can calculate the elevation difference A minus C and B minus D. And if in that case, we can say this value, non-zero value, will tell the value of theta. So we need these three values, and these three values will be calculated sum, azimuth difference, and elevation difference. So basically, the main aim is to calculate sum, azimuth difference, and elevation difference. These azimuth difference, elevation difference, and sum can be calculated using the comparator. So this process is done by the monopulse comparator. So this monopulse comparator is nothing but just a sum and difference network. So I will discuss this the whole monopulse comparator in the following slides. But before that, let me just tell you about the principle, how it is working. So in the first case, the target is right at the center. The target is right at the center. That means all the antennas will receive the same amount of echo. The green area you can see is same for all the antennas. In that case, the sum will be the maximum value. The sum will be the maximum value that will give you the value of R. But if you see the azimuth difference, that means A minus B and C minus D will be equal to 0. That will tell phi is equal to 0. And elevation difference is A minus C and B minus D, that will also be 0. That means theta will be 0. From this we can say that the target is right at the center. Suppose the target in the second case, I assume the target is off center in the horizontal plane or in the azimuthal plane. So in that case, what we can say, the green portion you can see, if the target is shifted on the right side in the horizontal plane or in the azimuthal plane, A antenna and C antenna will receive less amount of echo compared to B and D. So the green area just representing the echo. So in this case, if you see, B and D are receiving more compared to A and C. So if you calculate the sum is still the same. Sum will remain the same. There won't be any difference in the sum, because the location, because the R value is not going to change. Only the change is in the theta and phi. So if you calculate the sum, you will get the same value. You can easily find out the value of R. But to calculate the value of theta and phi, we have to calculate the difference. So we first calculate A minus B, and then we will calculate C minus D. And if you see, this value will be a non-zero value. And based on this non-zero value, we can actually say that this non-zero value will indicate the value of phi, right? And if you calculate the elevation difference will be still 0, because A and C have same amount of a green portion, you can say, the received echo. So the difference between A and C will be 0. The difference between B and D will also be 0. So you can say that elevation, because there is a no movement of the target in the elevation plane, so theta must be 0. So you can say the value will be 0 here. In the third case, we may assume that the target is shifted in the vertical plane or in the elevation plane. In that case, what will happen? A and B will receive the same amount of echo that can be seen from this green portion, and C and D will receive the same amount of echo. But the difference between A and C, that is the elevation difference, will be non-zero. And if you see the azimuth difference, because there is no movement in the horizontal plane, so the azimuth difference will be 0. So based on this azimuth difference, you can say the phi is 0. And based on this non-zero value, you can find out the value of theta. This theta will be given by this non-zero value. So if you combine the second and the third case, you can say that if the target is shifted in both the planes, in azimuth as well as elevation plane, in that case, what will happen? You will get both the values non-zero. You will get both the values non-zero, and based on this non-zero value, you can say theta and phi can be calculated from here, right? So you can easily find out the value of theta and phi, and to calculate the value of R, you have to just take the sum A plus B plus C plus D. That's it, and then you will get all the you can say the position of the target. So this is just the basic principle how monopulse tracking works, right? So in this case, in this block diagram, if you see, there are two you can say portion of this monopulse tracking. One is the antenna part, and another is the comparator part. So we'll discuss one by one these two parts. First, we'll discuss the antenna part, then we'll discuss the comparator part. But before discussing this antenna and comparator part, I just would like to mention how to choose a particular frequency, because there are design parameters we have to first fix the design parameters, right? We have to design any monopulse tracking system. We have to find out at what frequency we should design this system, right? So there are parameters. The first one is the frequency of operation. So this frequency of operation is very important, means how to decide at what particular frequency we should design the monopulse system. Monopulse antenna should be designed at which frequency, right? So actually this frequency of operation depends on various factors. The main thing is you have to check for what purpose you are designing your radar. Or you can say the function for which the radar is designed. Okay, so the radar is intended to perform some function, right? So based on that function, you have to decide your frequency of operation. The environment, the first one you can say the function the radar is intended to perform, and the second one you can say the environment the environment in which it is going to be used. So suppose the environment, I mean to say whether it is going to be used for shipboard application where you can say the weather will be very adverse. In that case we will have a different frequency, and or you can say the platform on which the antenna should be mounted, right? So the platform is also very important. The platform can be a ground-based platform, or it can be a shipboard-based platform, or it can be a aircraft. Right. Suppose we are talking about the aircraft application. So in the aircraft application, the size plays a very important role. Aircraft, we need a low profile antenna, and low profile antenna means we should go for a high frequency we have to choose, right? So basically this frequency of operation depends on this platform, whether that if we are designing an antenna for ground based application, so that we can have a radar can be placed in a ground based application. In that case the size of the antenna won't matter for us. In that case we won't be able to we want that more and more power can be transmitted. So in that case we can go for a lower frequency, right? We can go for a lower frequency, but if it is for aircraft application we will go for a higher frequency. So it all depends on for what applications we are designing the monopulse antenna. Similarly, there are other constraints are there, like bandwidth is there, side lobe level is there, physical size and weight. Physical size and weight actually depends directly on your requirement. Suppose you are designing for ground based application. Ground based application, we can have we will have a more space. We can easily work on low frequency. Low frequency means more size. More size means uh, weight will also be more, but the advantage of more size will be you can transmit more amount of power. So power handling depends directly on the size of the antenna. If the size is more, you can transmit more power. So in aircraft application, suppose for aircraft application, we have to work for a low profile antenna. Basically for we have to work at higher frequency. If you work at higher frequency, so the constraint will be here power handling. Power handling will not be much. And this power handling, if you are able to transmit less amount of power, so the basically the range of the target will also be limited, right? So there are restrictions. Suppose for shipboard application. In shipboard application, we have to mount our monopulse antenna over the ship, and the two things are there. One is the frequency. Frequency, we cannot go beyond a certain particular frequency, because if we go for higher and higher frequency, the attenuation will also be more, and we won't be able to use for long range applications, right? So another factor will be this. If we go for a lower frequency in shipboard application, the size will be the constraint. So if you use for low frequency, then size will be more, and that more size will be very difficult to mount on the shipboard application. So we have to actually compromise. We have to basically check for which application we are using. Similarly, gain and beam width. Gain is also directly depends on the normalized size of the antenna, right? If the size of the antenna is more, gain you can get more of the antenna. And of course the gain will tell the the range of the target also. So beam width is also one of the important parameter in this case. If you want to achieve the same beam width, if you want to achieve the same beam width from a low frequency antenna, then you have to have a much more size. Okay, and the same amount of same value of beam width can be achieved at higher frequency with a less size. So it it all depends on the applications. Suppose we want 10-degree beam width or 5-degree beam width. So we can achieve the same beam width if we are working at lower frequency. If we are working at ground-based application, we have to go with a higher size. More and more size will be increased. But if we are working for aircraft application, the same amount of beam width can be achieved with less size. So it all depends. So all the parameters actually connected with each other. Like a polarization. Polarization is also one of the parameter, whether it is a linear polarization or circular polarization. And the last one, which is which tells the accuracy of this monopulse system, is the null depth. Null depth is actually tells you how much accurately the difference has been calculated. Because as I told you, we are using 4 antennas in monopole system, and all those four antennas must be similar in characteristics. Means the gain of the antenna. All these 4 antennas must be similar. If those antennas are not similar, what will happen in that case? Even if the target is right at the center, A minus B and C minus D, or A minus C and B minus D will not be equal to 0, even though the target is right at the center. But these antennas are not similar, so we will not get exactly 0 value. So this null depth is actually tells you how much accurately this difference has been calculated, assuming the target is right at the center. Okay, if the target is right at the center, ideally we should get this value as a 0, but ideally nothing, in reality there won't be a 0 value. We'll get some value of minus 30, minus 35 dB, like we optimize for S parameters. S11 we generally keep it minus 10 dB, less than minus 10 dB. So standard value for this null depth is we generally keep it minus 30 dB. So less than minus 30 dB is basically, you can say, 10 to power minus 3 value, 1 by 1000. So we can say it is a good null depth, right? So these are the factors we have to actually keep in mind before designing, or before designing our monopulse antenna. So now I will be discussing the monopulse antenna that was supposed to be deployed on aircraft. So for aircraft application, as I told you, the profile is a major constraint. The size of the antenna is major constraint here. The restriction is on the size, so we have to go with a low profile antenna. So low profile antenna is you can say the microstrip antenna is as the low profile. But with the disadvantage of a microstrip antenna is that it gives you a very narrow bandwidth. So to increase a bandwidth of the simple micro, this one, first one, this structure is a microstrip antenna. If you see this is designed at X band. This is designed at X band, 8 to 12 gigahertz, basically 8 to 12 gigahertz, and our particular frequency was 9.3 gigahertz. It was designed at that particular frequency, and the substrate that we chosen was this RT Duroid 5880, whose thickness is 0.78 millimeter, and the dielectric constant is 2.2, and the loss tangent is 0.001. So if you see, this is the side view and this is the top view of the microstrip antenna. This is the coaxial feed is given. This is the SMA connector. The inner is connected to the patch, and the outer is connected to the ground plane. Right. So in this way, we can design and simulate using any software like i3D, or you can design it using CST or HFSS. You can use any of the software, and all the design details have been given here. This is the off center. This is the center of the patch antenna, and at a position of 1.4 mm from the center, the feed is given just to have a impedance matching. Right. So 50 ohm somewhere we will get at 1.4 mm, so that you can see this black curve. This black curve is actually the reflection coefficient for this microstrip antenna. The size of this microstrip antenna is 10.2 by 10.2. So this is actually a square microstrip antenna, right? And this is the results. And if you see the bandwidth that has been obtained for minus 10 dB reflection coefficient is approximately 250 megahertz, which corresponds to the 3% bandwidth. So bandwidth for this microstrip antenna is a major disadvantage. So it gives you a very narrow bandwidth. So, but there are many techniques to improve the bandwidth of a microstrip antenna. there are various technique, but in my case I've used this electromagnetically coupled microstrip antenna. So EMCP technique actually improves the bandwidth, you can say, significantly compared to the simple microstrip antenna. In EMCP microstrip antenna, this dotted curve, red curve, is gives you the bandwidth of, or you can say the reflection coefficient for EMCP microstrip antenna. And if you measure the bandwidth for this is varying from 8.25 to 10.25 approximately, which is around 2 gigahertz. And if you calculate in terms of percentage, it is 21%. So it is a very, you can say, significantly difference between this bandwidth obtained from the EMCP and simple microstrip antenna. So what is an EMCP microstrip antenna is, we have to use as it is, this is a simple microstrip antenna as it is. On above of that, we have to add one more substrate. One more substrate we have to add, and we have to put one parasitic patch. This parasitic patch will be kept at some air gap distance. This distance has to be optimized based on our requirement. Actually, it will depend how much coupling we want from the active patch. This is known as the active patch, which is directly fed from the SMA connector. It is directly fed, and the upper patch is known as the parasitic patch, which is EMCP coupled with respect to the active patch. So this distance, the air gap between these two patches actually determines the coupling between these two. And this coupling, actually, if you see, there are two resonant frequencies are coming. One is around this 8.75, and another is coming at 9.75. So these two resonant frequencies actually coming, one because of this patch and another is because of this patch. This we can actually control based on our requirement of VSW, or basically you can say the matching and the bandwidth we want. If we want more bandwidth, we can change this air gap, and instead of this type of plot, we may get something like this. We may get like this. But in that case, what will happen? The matching will be poorer. So you have to compromise somewhere in terms of bandwidth, and in terms of if you further increase the gap between these two patches, it may happen that you may get a dual band like this, right? So you have to compromise. You have to means design accordingly based on your requirement. You have to optimize this gap. So we have used the same substrate for both the patches. You may use a different type of substrate in the in this case also, and based on that you have to change the design dimensions of the upper patch, like that, right? So this is the way to design EMCP microstrip antenna. And if you see, the bandwidth that we obtain is 21%, and this is the gain plot. This is the gain plot for a microstrip antenna where we have used only one active patch, and this is the gain plot for EMCP microstrip antenna. If you see, the gain difference is also approximately 2 dB. Approximately 2 dB improvement compared to the peak value, right? In case of a simple microstrip antenna, the gain is around 6.9 dB around, and in that case we are getting 8.88. So basically you can say approximate improvement of 1.9 to 2 dB in the gain as well. The gain is improved because we are using two patches, right? And so in our case, because we are getting more bandwidth using this EMCP and more gain, so we have used this antenna as a unit element for our monopulse antenna. So monopulse antenna, for designing a monopulse antenna, we will be using this EMCP as a unit element, and we will form the array. Array is formed just to increase the gain of our antenna, right? So first we have to design a unit element, and then we have to design the array of this antenna. The array of the antenna can be designed in multiple ways. We have many feeding techniques. We can use a corporate feeding technique, or we can use a series feeding technique. In my case, I have used a corporate feeding technique. There is a difference between the corporate feeding technique and series feeding technique. In the corporate feeding technique, all the elements will get equal amount of power. Suppose this is the corporate feeding technique, where this is a one unit element and this is another unit element. So in this way, and this is the center. This is the center of the feed. So here we are going to feed. Half amount of power will go in this direction. Half amount of power will go in this direction. Further, the amount of power will be divided into two parts. From here, it will be divided again into two parts. From here, it will be divided again into two parts. So at the end, basically, if the number of elements are 4 by 4 elements are there, so it means there are total number of 16 elements. So all the elements will get 1 by 16 of the total power, input power, right? So all the elements will get same amount of power if we in this corporate feeding technique. In the series feeding technique, basically, generally we use one element in this way and we connect like this. This is the series feeding technique. In this case, we are feeding in the center element, and these elements will get power from here. So as we are going away from the center element, the power will be getting reduced. So in that series feeding technique, what will happen? The current, or you can say the power distribution, will be a tapered form. But in this case, the power distribution is equal, uniform distribution is there. So you can say this is a in corporate feeding technique, we have designed a uniform distribution. All the elements have been given equal amount of power. So there is a difference why we are using in this case. So if you use this type of series feeding technique, the bandwidth will be affected in series feeding technique. Because of the phase delay, because of these discontinuities, and the phase delay will come into the picture, and the bandwidth will reduce. In case of the corporate feeding technique, bandwidth will remain almost same as we are getting for the unit element. That we can see from the results also. And there are some other things. The difference between the corporate feeding and the series feeding is that in the series feeding, as you can see, the distribution is non-uniform, or you can say the tapered distribution is there. Taper distribution is having its advantage of less, you can say, side lobe level. Side lobe level will be reduced in this case. But in corporate feeding technique, we'll get a side lobe level of approximately minus 12 dB to minus 13 dB. In case of series feeding, you can go up to minus 20, minus 23, or even more. You can reduce the side lobe level. So, but the disadvantage of series feeding technique is the gain will be less, because we are not utilizing the entire area of the antenna. So this is the actual, you can say, the area which is used. In this case, the area which is used is the entire rectangular area we are using. So you can say the gain will be less in case of the series feeding. The gain will be more in the corporate feeding. So there are other differences also. In our case, our focus was not the side lobe level initially. Our focus was the gain and the bandwidth. So in our case, we use the corporate feeding technique, and this is the feed network. This is the feed network. This feed network is how we have to design the feed network. First, we have to design the unit element. First, we have to design a unit element. Once you design the unit element, you have to check how much impedance is at this position. Once you check the impedance using software, you can put here some port, a discrete port here, and then you can determine how much impedance is at this position. Once you determine that impedance at this position, then you can take another, suppose this is one patch unit element, you can take another element and you can combine them. You have to combine in such a way that at the center, while feeding, we must get a 50 ohm, because the input generally we give using a 50 ohm connector, right? So if we want here 50 ohm, this basically we are connecting two lines here. Two lines are connected in parallel. That means this characteristic lines, sorry, this transmission microstrip line must have a characteristic impedance of 100 ohm, right? Then only we can get a 50 ohm, because two lines when connected in parallel, 100 and 100 will give you 50. So we have to if here also two lines are connected, if this impedance, if you don't convert 100 to 2, this impedance is also some 200 or 200, something like that, then we will get only 100. 100 is possible only like that, right? So there are actually various ways to get 50 ohm here. In my case, what I have done, I have means obtained this 50 ohm by considering this as a 100 ohm, this as a 100 ohm. Then this 100 ohm is converted using this lambda by 4 transformer. In this, if you see, this line width and this line width is different. If we see, the Z impedance is inversely proportional to the width of the microstrip line. If the width of the line is more, the impedance will be less. So in this case, if you see, this width is more compared to this, and that means this impedance is less. This impedance is approximately, I think, 70.7 ohm. And this is a lambda by quarter wave transformer. The quarter wave transformer, if you see, the quarter wave transformer is lambda by 4 transformer, whose length is lambda by 4. If the terminated impedance is ZL and if the characteristic impedance is Z naught, then the input impedance of this will be equal to Z naught square upon ZL. So you can easily calculate the input impedance. So using this equation, you can convert 100 ohm to any value. This is 70 ohm, this is 100 ohm. So basically you can say 70 into 70 upon 100, which will give you approximately 50 ohm, right? So it will give you approximately 50 ohm. 70.7 into 70.7, you'll get approximately 50. So basically we have converted into 50 ohm, and again there are two lines are connected. This must be also in such a way that here we should get a 50 ohm. So basically this must be 100 ohm, this must be 100 ohm. So if you connect these two lines, you will get 50 ohm. 50 ohm will be converted into 100 ohm. Again your same lambda by 4 quarter wave transformer will be used, and whose value will be 70.7 ohm. This will convert 100 ohm to 50 ohm. This 50 ohm, we are getting here 50 ohm. Sorry, we are getting 50 ohm here. That means this is 100 ohm. This is 100 ohm. Again, you have to convert 100 ohm to 50 ohm. 50 ohm. 50 ohm here. That means this is 100. This is 100. Again, you have to convert. So at the end, basically, you have to match your this impedance of the patch with this 100 ohm. So suppose this is 100 ohm, you have to use this lambda by 4 quarter wave transformer whose characteristic impedance should be such that the impedance seen here must match with the impedance of the patch or the unit element. Okay, so in this way you can design. There are a number of ways to design this feed network. I just given one example that you can convert 50 to 100 ohm, and you can use a lambda by 4 quarter wave transformer, right? So after designing this 4 by 4 array, this is the top view actually, and this is the side view. This is side view. If you see, the active patches are connected. Yeah, these are the active patches, and this is the SMA connector given at the center. So this you can say this is the center, and these are the parasitic patches which are EMCP coupled with respect to the active patches. So whatever the connection, this feeding network is there, it is on the active patches only. There is no feeding network on the parasitic patches. It is not required because these parasitic patches are excited using this active patches. Okay. So the power will be given, the input will be given at the center, and it will be divided equally among all the elements. And these are the results. And if you see the results of this 4 by 4 EMCP microstrip antenna array, you will see the bandwidth is approximately same that we were getting. In this case, we can say the bandwidth is approximately 17%. We are getting using this 4 by 4 EMCP array. And the gain, if you see the 19 dBi gain we are obtaining. If we see for one unit element, the gain is approximately 8.8 dBi, right? So if you apply the concept of antenna theory, 8.8 dBi gain is obtained using one element, right? And how many elements we are using? 16 element. If you double the element, the gain will be increased by 3 dB, because you have to see that 10 log doubling the thing will be equal to 3 dB, right? You have to add 3 dB if you are using two elements. So if the one element is giving you a gain of 8.8 dBi, then the two element should give you the gain approximately 11 point this 8 dBi. And in this case, we are using 16 elements. So basically, you can say 1 by 1 array is giving 8.8, 1 by 2 array is giving 11.8, and then 2 by 2 array will give you 14.8, and then you can say 2 by 4 will give you 17.8, and then 4 by 4 will give you approximately 20.8 dBi. But in our case, we are getting 19 dBi. So there is a difference. This is actually the calculation done using the concept of antenna theory. But in practically, you will not get the exact same value. Why? Because there are feeding losses also. So whatever the feeding network we have used, there will be some radiations will happen because of these feeding lines. Because if you see, these lines are having some finite width, so this will also radiate, and these radiations will be undesired. These radiations will not be desired. So it is always recommended to use a characteristic while designing a feeding network. It is always recommended to design to use a microstrip line with high impedance. If you use a characteristic line which is having high impedance will have a less width. Less width means it will radiate less. So undesired radiations will be very less. So you can somehow reduce the losses, right? So if you use suppose instead of using 70 ohm, if you use 30 ohm, the width will be further more, and it will further reduce your gain because of the feeding losses will be more, right? So it is always recommended while designing the feed network, you always choose a value of the impedance which is a little higher, okay? But don't use much high value, because if you use a very high value, suppose 200 ohm you are using, it will be very difficult to fabricate also, because for 200 ohm approximately the width will be 0.1 mm or 0.05 mm, something like that. So width will be very less, and it will be very difficult to get that particular for from a normal fabrication process. It will be very difficult, right? So it is always there is upper limit and the lower limit also, right? Lower limit is mainly because of the feeding losses, and the upper limit is because of this fabrication issues, right? And so this is the gain plot that we can see, and the 19 dB gain has been obtained, and the reason is only the losses are because of the feeding losses, and there are some losses in the substrate as well, because substrate is having some loss tangent 0.001. We have used RT duroid substrate, which it is very less lossy. So we can say the main losses in our antenna is because of the feeding losses. And in this case, the radiation pattern, if I have not shown here the radiation pattern, I'll show you in the next slide. But if you see the side lobe level that can be obtained using this 4x4 corporate feeding network is a minus 12 dB, because we are using a uniform feeding, right? If we use non-uniform feeding, then in that case you will get better side lobe level, but other things are there that you will get less gain, right? Right. So this is a 4x4 EMCP array using corporate feed. Then because we are going to use four antennas, we are going to use four antennas in our monopulse antenna, right? Four similar antennas, and we are going to use a circular structure we are going to use. So basically one quarter of the circle will be acting as a one antenna, another quarter of the circle will be another antenna, and like this we will form a circle. So four antennas, one is A, another B, C, and D. So basically the 4x4 network that we designed is rectangular in shape, but we want the shape of the antenna should be one quarter of the circle. So we wanted to have some shape like this. So what we did to get the shape of like a quadrant of a circle, what we did, we added some elements in series. So we are getting actually two advantages. One is already we have a corporate feeding network where we are getting SLL side lobe level of minus 12 dB. But to improve the side lobe level, what we can do, we can add some elements in the series. So this is actually helping us in obtaining more better side lobe level, and making our structure quadrant structure, right? In one fourth of the circle, you can see in this form, right? So it is giving us two advantages. One is we are getting more improved SLL. So by adding this element in series, so these elements which are added in series in the right side and in the upper side, if you see here also we have added three elements. Here we have added two elements. So if you see after adding these elements, the bandwidth is approximately same that we were getting in, because we have only added these elements at the end, and these elements only added at the parasitic case, not at the active cases. Okay, so these are only added at the parasitic layer. So here if you see up to this, the active patches is there, and after this these are the series elements that we have added on the parasitic layer. From the side view it is more clear, right? So this is the S parameter reflection coefficient results, and this is the gain is approximately same as we were getting for 4 by 4. In 4 by 4 we were getting 19.1, here we are getting 19.3. So little bit gain is improved just because we have added few elements in series. And if you see the side lobe level, the side lobe level is improved to minus 15 dB. So it is improved by a value of 2 to 3 dB compared to the corporate feeding technique. And this improvement is because we have added these elements. And this can be seen from this radiation pattern. Here, if you see the radiation pattern shows the this side lobe level compared to the main lobe is minus 15 dB. right? So this improvement is because of the series elements that we have added. But if you notice, this radiation pattern is asymmetric. It is not symmetric in both the planes. If you see, this is not symmetric with respect to this axis. Why this is not symmetric? Because we have added the elements only on the right side and the upper portion. We have not added here. We have not added the elements here. We have not added the elements in the left side, right? We have only added the elements on the upper portion, in the top side and on the right side. So that's why, because this antenna is itself not symmetrical, so that's why we are getting asymmetry in the radiation pattern. But this is not a problem for our monopulse antenna, because we are going to use this antenna, this EMCP MSA array with hybrid feed. Why I have written here hybrid feed? Because it is a combination of the corporate feed and the series feed. So basically we are using the hybrid technique to design this antenna. And this asymmetry will be compensated while integrating four antennas in this circular fashion. So one will be installed here, another will be here, third one will be here, and fourth one will be here. So it will form a circular symmetry in that case. In that case, if you see, the radiation pattern will be symmetrical. So this asymmetry is only for the unit element, unit antenna element, or you can say antenna A will be a symmetric radiation pattern. Antenna B will also be asymmetric in radiation pattern. Similar for C and D. But when you combine all these antennas in the form of a circular structure, then the antenna will be symmetrical, and the radiation pattern will also be symmetric. We will see once we integrate the antenna with the monopulse comparator, and at the end of the discussion, we'll see the results will be giving you a symmetrical radiation pattern. So I have discussed till now. I've discussed the antenna portion, the antenna part, the radiating part of the monopulse system. Now the second part of the monopulse antenna is monopulse comparator, which will be calculating the sum and the difference. If we want to calculate if we want to track the target in one plane, either in azimuth plane or in vertical plane or elevation plane, then in that case we only need two variables, two values, two parameters, r phi or r theta. But in case if we want to track the target in the space in 3D, we need three parameters, three parameters, r, theta, and phi, right? So for single plane, actually we need only two antennas. As we have seen in the concept of sequential lobing, there were only two beams were required. So similarly in monopulse antenna, if we have to track a target, we need only two antennas, antenna A and antenna B, for tracking the target in one plane. But if we want to track the target in both the planes, we need four antennas, right? So this is the and theta or phi. In this case, you are using two antennas, and we are calculating the sum and the difference. So basically, we have to somehow we have to design one sum and difference network. Sum will give you the value of r, and the difference will give you azimuth value theta, or it will give you the phi value. But this is for the single plane. But for dual plane, we need four antennas: antenna A, antenna B, antenna C, antenna D. And to calculate the sum and the azimuth difference, elevation difference, we will require four sum and difference network. In this case, only one sum and difference network was required, but to track the target in both the planes, we will need four sum and difference networks. So you can see, first the antenna A input and antenna B input will go to one sum and difference network. From there, we will get A plus B, A minus B. Similarly, from C and D, the input will go to another sum and difference network, the second sum and difference network, which will give you C plus D and C minus D. This A plus B, C plus D will act as an input to the third sum and difference network, which will give you here the sum, which will be A plus B plus C plus D, and it will give you the difference, that is the azimuth difference, A plus B minus C plus D. Similarly, the difference values will also be acting as an input to the fourth sum and difference network. It will give you the elevation difference and the diagonal difference. This diagonal difference, as of means in our case, is not required. But if you keep it open, then it will reflect whatever the power is going in this direction. If you keep it open, it will reflect back and it will interfere with our other circuit part, right? So better always recommended to connect it with a match load. Okay, so this will be connected to a 50 ohm match load, so that whatever the power is going in this direction, it will be absorbed in this 50 ohm, and nothing will reflect back, and it will not interfere with other parts of the circuit, right? So basically, to design a monopulse comparator, what we need four sum and difference networks. How to design a sum and difference network? If you see the working principle of a waveguide magic T, it can act as a sum and difference network. If you give in the waveguide magic T, there are four ports. If you give the input at two of the ports, other two ports will give you the sum and the difference. Similarly, the branch line coupler can also act as a sum and difference network if we introduce a 90-degree phase delay line at one of the input of the branch line coupler. In that case, also we can use that branch line coupler as a sum and difference network. The third option is the rat race coupler. The rat race coupler can also act as a sum and difference network. I'll discuss all these three one by one and their advantages and disadvantages as well. So the first one is the monopulse comparator using folded waveguide magic T. So this is the conventional waveguide magic T. If you see, there are four ports: port 1, port 2, port 3, and port 4. This port 3 is also known as H arm, and this port 4 is known as a E arm. Basically, if you give the input at port 1 and port 2 simultaneously, then you will get a 1 plus 2 at H arm, and you will get 1 minus 2 H at port 4. So basically, it will give you a sum at the port 3 and the difference at the port 4. So that's why we can say that a waveguide magic T can be used as a sum and difference network. So what we can do, we can connect this port 1 to the antenna A, and we can connect the port 2 with the antenna B. So if we give, if whatever the echo we have received in antenna A and antenna B, we can get the sum at this port and the difference at this port. And based on this sum, we can calculate the value of R, and based on this difference, we can calculate the value of theta or phi. So this is the case when we have to track the target in one plane. Okay, but if you have to track the target in both the planes, we have to integrate four waveguide magic T's. Uh, but this conventional waveguide magic T has a disadvantage of that E arm is a vertical arm is like this. So it is occupying more space, and to make it compact, what we can do, we can fold it. So this waveguide magic T is also known as a folded waveguide magic T. So this fourth arm is folded in such a way that the electric field distribution will remain same, so it won't change anything, right? So if you give the input at port 1 and port 2, still you will get 1 minus 2 here and 1 plus 2 here. Okay, so it is folded, and so it is named as a folded waveguide magic T, which occupies less space compared to the previous one, right? So this can be used as a sum and difference network for tracking the target in one plane. But if we want to track the target in both the planes, we have to integrate four of these waveguide magic T's in such a way that if you give the input at port 1, 2, 3, and 4, the other four ports, port 6, 5, 6, 7, 8, will give you the sum and difference. So you can see this is a one waveguide magic T, this is the another waveguide magic T, this is the third one, and this is the fourth one. So four waveguide magic T's have been integrated, interconnected in such a way that if you connect port 1 with antenna A, port 2 with antenna B, port 3 with antenna C, and port 4 with antenna antenna D, then you will get sum at the port 7. These outputs have been written here. You can see, and other azimuth and elevation difference you will get at port 6 and 8. And the port 5 will be giving you a diagonal difference is not required, so you can actually connect it with a matched load. So these three outputs actually required for calculating the value of r, theta and phi. So this can be used, but the thing is, in our case, this was supposed to be designed for the aircraft application, and the waveguide is very bulky and occupies more space as well. So instead of designing a waveguide magic tee for our monopulse comparator, we have chosen a microstrip, or you can say the planar geometry for that monopulse comparator. So the planar monopulse comparator can be designed in two ways, using a branch line coupler with by adding a 90-degree phase shift delay line. This is the basic, you can say, the branch line coupler, where if we give the input at port 1 and the port 2, the output will be out of phase by 90-degree. That can be seen from this S parameter matrix. If you see, S13 and S14 are out of phase by 90-degree. This is 180-degree, this is 90-degree. So basically the out of phase by 90. Similarly here, this is J, this is -1. That means these are out of phase by 90-degree. So as if you use directly the branch line coupler, we cannot get sum and difference. So somehow we have to introduce a 90-degree phase delay line either of one of the input port. We can add 190-degree phase shift at port 1, or we can add at port 2. In our case, I have added a 90-degree phase delay line at port 2. Instead of a straight line, I have added a U-shaped line so that we can make it compact little. Right, so we have used a U shape 90-degree phase delay line. 90-degree phase delay line is basically the length is equal to lambda effective by 4. So basically this length, the total length is lambda by 4. And compared to this, if this length is L1, then this entire length is L1 plus lambda by 4. So basically we are adding 90-degree compared to the port 1. So if you add 90-degree here, this is 90-degree. This length is also 90-degree. So if you see from port 1 to port 4, the angle is 90-degree, or you can say the delay is minus 90-degree. From port 1, this is port 1, for port 1. From port 1 to port 3, how much difference is there? This is a 90-degree, this is a 90-degree, that means 180-degree. 180-degree is for port 1. What about the port 2? From port 2 to port 4 is how much difference is there? This is a 90-degree, this is a 90-degree, this is a 90-degree. 90, 90 and 90. How much it is? 270. So 270-degree for port 2. Similarly, from port 2 to port 3 is how much difference is there? 90-degree and 90-degree. This total is 180-degree. 180-degree for port 2. So if you see, the output at port 3 is in same phase for port 1 as well as 2. So here you will get the sum. Here you will get the sum, because both the outputs at port 3 are in same phase. Here if you see the output at port 2, one is minus 90-degree, another is minus 270-degree. So there is a difference of 180-degree between the two outputs. So at port 4 you will get difference that you can see from the S parameter matrix as well. So if you see -1, that means both are adding. So basically you will get a sum at port 3. This is port 3, this is port 4. So basically this is 1, this is 2, this is 1, 2, 3, 4. So here you are getting -1, both are in same phase. That means at port 3 you will get the sum. At port 4, if you see J, here the J term is coming, here the minus J term is coming. So there is a difference of 180-degree. That means you are getting the difference at port 4. So if you add 90-degree delay line at one of the input port, you can add at port 1 also. Then you will get sum at port 4, difference at port 3. If you add at port 2, as I have done, in that case you will get sum at port 3, difference at port 4. Right. So this basically I just want to let you know that the branch line coupler, by adding just a 90-degree phase delay line, can act as a sum and difference network. Right. So this can be used in monopulse comparator for one plane tracking, but for tracking the target in both the planes, we have to interconnect four branch line couplers of this type of branch line couplers, which have which has this one lambda by 4 90-degree delay line. So if you see, this is a one branch line coupler, this is the another branch line coupler, this is the third one, this is the fourth one. So if you see, if you connect the port 1 uh, with the antenna A, port 2 with antenna B, port 3 with antenna C, and port 4 antenna D, then the other 4 ports will give you the sum and the difference. So port 8 is giving you the sum, port 7 is giving you the azimuth difference, port 5 is giving you the diagonal difference, and port 6 is giving you the elevation difference. And that can be seen from this as parameter matrix also. This is port 1, this is port 2, this is port 3, 5, 6, 7 and 8. If you see here 8 port is giving 1 1 1 1 1 1. That means all are in same phase. So basically you will get A plus B plus C plus D, right? So basically you will get the sum at port 8. Similarly, if you see at port 7, first two are minus J, the second two are plus J. So there is a 180-degree phase difference between these. So basically you will get the azimuth difference. This is defined as an azimuth difference. So at port 6, if you see, this is minus J, this is minus J. These two will be added. This is a plus J, this is a plus J. These two will be added, and there will be, you will get a difference. That is known as the elevation difference. And this if you see, the minus 1, this is plus 1, this is plus 1. So these two will be added, these two will be added, and we'll get a diagonal difference. So our aim, our requirement is only some azimuth difference and elevation difference. These three are the required. The other one will be connected to the match load. So basically, you can use this branch line coupler by adding 90-degree phase delay line as the sum and difference network, and you can design your monopulse comparator. So this is the monopulse comparator designed using branch line coupler. But the disadvantage of using this branch line coupler is because we are adding 90-degree phase delay line, somehow it will limit the bandwidth. It will limit the bandwidth of our monopulse comparator, because we are using lambda by 4 delay line as well, right? So it will limit our bandwidth. These are the results at different ports. This is the VSWR. VSWR plot at the input port. Input port we are assuming 1 to 4, and this is the VSWR plot for output ports. We are assuming 5 to 8. And if we see the bandwidth that we obtained for VSWR less than 1.5 is 14%. And the isolation between the sum to difference and difference to difference means sum port to the difference port. Sum port is the port 8 and difference port is 6 and 7. So basically S68 or S78, this is the isolation. So that you can see from here, S68 and S78, these two are the isolation sum to difference. And what is the difference to difference? Difference port is, one port is 6 and another port is 7. So isolation between 6 and 7, that is known as X67. So this X67 is given by this plot. And this isolation is very good. If you see, the isolation is better than 30 dB over the 14% of bandwidth defined. And sum to difference isolation is also better than 15 dB. Right? So this was designed using a branch line coupler. Then the third that we can design a monopulse comparator using rat race. What is a rat race? The rat race is a very simple configuration. If you see here, there are 4 ports: port 1, port 3, port 2, and port 4. This length is lambda by 4. This length is lambda by 4. This length is lambda by 4, and this length is 3 lambda by 4. So the total perimeter of this circle is 3 lambda by 2. 3 lambda by 2. And in case of branch line coupler, if you see, the branch line coupler is having different impedances. Here the impedance is 35 ohm, here the impedance is 50 ohm, ZA, ZB. So if you calculate these impedances using even and odd mode analysis, this will give you 35 ohm, this will give you 50 ohm. Right? The different impedance values you are getting, which will limit, because of the variations in the impedance, bandwidth will reduce. But in case of the rat race coupler, if you see, the entire parameter is having the same impedance, and this parameter impedance is 70.7 ohm. That can be calculated using even and odd mode analysis. By having a line of symmetry like this. Okay, so you can do the even and odd mode analysis and calculate the value of this impedance of this circle, this microstrip line, and that value will be 70.7 ohm. If you see, there are no variations in the impedance in the entire circle, right? So in that case, if you see the bandwidth, you will get more than the branch line coupler. This is one of the reason that you can get the more bandwidth compared to the branch line coupler. So how it actually working? If you give the input at port 1, what is the difference from port 1 to port 3? 90 degree. This is the lambda by 4 distance. So lambda by 4 difference means minus 90 degree for port 1. And what about port 1 to port 4? Port 1 to port 4, there are two paths. One is the upward and one is the downward, and both the paths are having equal length. Equal length means 3 lambda by 4. 3 lambda by 4 means 270 degrees. So basically you will get minus 270 degree for port 1. And what about the port 2? For port 2, you will get here from port 1 to port 2. This is you can say there are two paths. One is having a 180 degree and another is having uh, uh, this is a 270 plus 360 degree. So basically if you give input at port 1, nothing will come at port 2, because there are two paths. One is this path, another is this path. One path is giving you 180 degree, another path is giving you 360 degree. So you will get nothing at the port 2. So basically the port 1 and port 2 are isolated. Similarly the port 3 and port 4 are isolated port. So if you give the input at port 1, you will get the output at port 3 with minus 90 degree phase shift, and you will get the output at port 4 with minus 270 degree phase shift. What about the input if I provide at port 2 simultaneously? If you give the input at port 2 from port 2 to port 3, how much is the length? Lambda by 4. So basically from port 2 to port 3, the output will be minus 90 degree, right? And from port 2 to port 4, how much is the difference? 90 degree. So you will get 90 degree for port 2. And from port 2 to 1, you will not get anything because these two ports are isolated. So basically if you see at port 4, we are getting two outputs, and these two outputs are out of phase by 180 degree. 180 degree means there is a difference. So basically at port 4 we will get 1 minus 2. And what about port 3? Both the outputs are in same phase, minus 90 minus 90. That means we are getting here sum, and that can be seen from the S parameter matrix. So you can see this is port 3 plus 1 plus 1, both are in the same phase. It means we are getting sum at port 3. So we are getting sum at port 3. Here you are getting minus 1 plus 1. It means we are getting the difference of these two. So difference is getting at port 4. So basically this rat race coupler can be used as a sum and difference network. And one more advantage of using rat race coupler, you can any of these two ports you can use as an input port. You can use 1 and 2 as an input port, then 3 and 4 will give you sum and difference. You can use this one, or you can use 3 and 4 as an input port, then 1 and 2 will give you sum and difference. So this is the advantage of using rat race coupler over branch line coupler. In branch line coupler, this will not be the scenario. You cannot reverse it. If you see this port 4, if you give the port 4 and port 3 as an input, you will not get sum and difference. That can be seen from here. That can be seen from here. This matrix is not like this, right? You are not getting sum and difference at port 1 and port 2. But in rat race coupler, this is, you can say, reciprocal. You can use 1 and 2 as input, or you can use 3 or 4 also as an input. So this is one of the main advantage of rat race coupler also. You can say additional advantage of rat race coupler over branch line coupler. So you can use any of the two ports as an input port and any other two ports as output ports in case of rat race coupler, but this is not the case of a branch line coupler. So this rat race coupler actually can be used as a monopulse comparator for designing or tracking the target in one plane. But if you want to track the target in both the planes, you have to connect the 4 of these rat race couplers in such a way that if you connect this port with antenna A, this port with antenna B, this port with antenna C, this port and with antenna D, if you connect, then other 4 ports will give you sum and difference. This is the port 1, this is the port 2, this is the port 4, this is the port 3. So these 4 ports will give you the sum and the difference. So that can be seen from here as well. The port 1, I think this is a port 1, this is a port 4. Yeah. So you can see at port 1, we are getting sum. All values are same. 1 plus 1 plus 1 plus. So A, B, C, D, we are getting the sum of this. Here at port 2, we are getting first 2 as a negative, another 2 as a positive. That means we are getting the difference of these two. The difference that we have denoted with elevation difference. Right. Basically, what we are getting, 5 plus 6 at port 2, we are getting 5 plus 6 and 7 plus 8, and the difference of these two. So 5 plus 6 and 7 plus 8. That is that means we are getting the vertical difference. Vertical difference we have denoted with elevation difference, right? So at port 3 we are getting the azimuth difference. These two values and this value is added, this value and this value is added. So basically we are getting the azimuth difference. The fourth one is the matched diagonal difference, basically 5 minus 8 and 6 minus 7, that is known as a diagonal difference, and that can be connected to some matched load so that there should not be any reflection from that port. So this is a monopulse comparator actually we used for our design, and this we fabricated also. I'll show you the fabricated result. Before that, I'll just show you the simulated results. And if you see, the simulated results shows the VSWR plot at the input port, at the output port, and the bandwidth that can be obtained for this rat race monopulse comparator is 31% for 1.8 VSWR, and the isolation between the sum to difference and the difference to difference is better than 20 dB and the 40 dB respectively. If you see from these ports, you can see over the entire range of the bandwidth, this is less than 20 dB, and for this black curve, which is difference to difference, is better than 35 dB or 40 dB, right? Like this. So this rat race monopulse comparator was fabricated, and this is the fabricated photograph that you can see. This is the one. This is the second. This is the third one. This is the fourth one. So there are 8 ports are there. These ports are connected. These 4 ports are going to be connected to the 4 antennas: antenna A, antenna B, antenna C, and antenna D. Right. So these 4 ports will be connected to the 4 antennas that we are going to integrate in the next slide. I'll show you. And these other 4 ports will give you the sum and difference. And this fabricated results are shown here. This is the VSWR for the measured VSWR at input port, output port, and these are the isolation between the output port, sum to difference and the difference to difference. And simulated bandwidth that we obtained is 31%. The measured bandwidth is approximately 28%. There is a good agreement between these two results, measured results and the simulated results. And if you see, the measured isolation is also better than 18 dB for sum to difference, and difference to difference is better than 25 dB. So then after discussing these two, antenna part and the comparator part, what is the main task is to integrate the antenna with the monopulse comparator. So as I showed you, we designed EMCP with the hybrid technique. This is the one. This is the same antenna. This is the one antenna which we integrated with other 3 of the same type. This is the A, this is the B, then this is the C, and then this we have a D. So 4 of these antennas are integrated. How we integrated? We took the central point we have taken, and this central point where we were feeding to the antenna is connected to the port of the the comparator, the monopulse comparator. So basically, we connected the port, the antenna A here, antenna B here, antenna C here, and antenna D here. That you can see here in the side view. This is the side view of the structure. So basically, if you see in the side view, we have a 3 substrate here. 3 substrate. One substrate is used. This substrate is used for the active patch. This is the active patch, and this is the parasitic patch. And this substrate is used for that parasitic patch. And this substrate, the last one, the below substrate we have used is for the monopulse comparator. And this we have used a common ground plane, because the ground plane is required for comparator as well as the active patches, right? We need a ground plane. So what we did, we have inverted the structure of the monopulse comparator. So basically, the monopulse comparator was like this. This is the ground plane. This is the ground plane, and the monopulse comparator was designed over this. But we have inverted this. So basically, what we have done, this is the substrate, and over the substrate we have a ground plane, and here it is the monopulse comparator. You can see this green area represents the monopulse comparator. This represents the active patches. This represents the parasitic patches. And this is you can see the side view. All the substrate we have used, RT duroid substrate we have used. and this is the top view. In the top view also, if you see, there are three different color elements you can see. One is this one, which is a parasitic, this one is an active patch, and this green portion is representing the monopulse comparator. You can see here, this is a one rat race coupler, second rat race coupler, third rat race coupler, this is a fourth one. So this whole is connected, and which is integrating the four similar antennas, right? So after simulating this, we will get three outputs, three reflection coefficients, basically from the port, sum port, azimuth difference port, and elevation difference port. So if you see the result here, the S parameter, you can see from here for the all the ports, port sum port, difference port, and elevation and azimuth difference port. The bandwidth is coming around 21% for VSWR less than equal to 2. So these are the simulated results, right? And if you see the fabricated monopulse antenna, we fabricated this also, and I have shown the different views of the antenna. This is the bottom view of the structure. If you see this side view, this is the bottom view. Bottom view is what? The monopulse comparator that you can see here. This is the monopulse comparator. And if you see this is connected to the for measuring our sum port. This is the azimuth difference, this is the elevation difference. And if you see here, we have connected some load. This chip load is actually a 50 ohm. This is the 50 ohm load, because this output is actually a diagonal difference which was not required. So we connected it with the 50 ohm. So this is the bottom view. This is the top side of the middle substrate. So what is a middle substrate? Middle substrate is this one, and the top side of that is an active patch. So basically you can see the active patches, and you can see the corporate feeding technique is given to this. This is a 4 by 4 element. This 4 by 4 element. This is also 4 by 4 element. 4 by 4 array. This is also 4 by 4 array. So, and this is the bottom side of the upper substrate. What is the upper substrate? Upper substrate is this one, and the bottom side of this is parasitic element. And you can see clearly that these are the parasitic elements which are not connected to each other, but at the end we have added some series elements to make the structure circular. So if you see now, the structure is circular in this circle, and there was a diameter was given to us that we have to design the structure within that size. So we designed that within that size, and these are the fabricated results. This is the S parameter at some port. This is the S parameter S1, S you can say S22, azimuth difference port, and this is the elevation difference port. So these are the isolation between the sum to difference and the difference to difference, basically from port to 2 to 3, or 3 to 4, or 2 to 4, like that. And these are the gain plot, the simulated gain and the measured gain. So if you see by 4 by 4, by one 4 by 4 element array was giving us a gain of approximately 19.3 dBi, right? And we are using how many? 1, 2, 3, 4. So basically we are multiplying it with 4. Multiplying it with 4 basically should give you 6 dB more gain. 6 dB more gain means we should get 25.3 dB gain. But this is the actually the theory, as per the theory of you can say antenna theory, we should get a 25.3. But always there are some losses in the feeding network, and this monopulse comparator also will have some radiations, and because of those losses we will not be able to get the 25.3 dB. Instead we are getting how much is 24.3 dB. This is the gain, measured gain. So approximately we are getting the gain of 24.3 dB, and the isolation is better than 20 to 40 dB for sum to difference and a difference to difference. And the bandwidth that we have obtained is 21%. However, there are slight variations in the fabricated results, and we are getting 21% bandwidth due to some peaks are there here. If you see, there are few peaks are there where we are getting minus 8 dB. So BSWR is basically 2.3 in this range, and this is maybe because of the alignment issues, because we have to properly align all these three substrates, right? We have to properly align, and the at this entire design is done at X band, approximately 9.3 gigahertz, and the alignment should be very proper at that particular frequency. Even a small misalignment will give you this type of the means the less accuracy compared. There will be measured, and you can say the measured results will not match exactly with the simulated results due to this misalignments, right? So this is all about the S parameters isolation and the gain. But what I want to show you now is the simulated radiation pattern, because if we have seen that the radiation pattern was not symmetric for one antenna, but when you integrate, if you integrate the radiation pattern, it is almost symmetrical in both the planes. If you see, this is the simulated sum azimuth, this is the measured sum azimuth, this is the simulated sum elevation, this is the simulated sum elevation. Basically, this is you can say E plane, this is H plane. Similarly here, the difference azimuth, this difference elevation. So there will be four radiation patterns that we have to see. Two for the sum, and one is for the azimuth difference, and the another one will be for the elevation difference. And from the difference pattern, we have to see how much is the null depth, and from the sum pattern we have to see how much is the side lobe level. So side lobe level, if you see, is approximately minus 15 dB. This is the line for minus 15 dB, and we are getting approximately minus 15 dB side lobe level. And this is because we have added few elements at the end in series. So because of the series elements, we are getting 15 dB. If you don't add those elements, then you will get approximately 12 dB SLL. But we have added, so we are getting a better side lobe level. And null depth is you can see here in the elevation difference at 0 degree. We are assuming the target is right at the center at 0 degree for elevation plane, as well as for azimuth plane. So basically we are assuming theta is equal to 0 and phi is equal to 0. So if theta is equal to 0 and phi is equal to 0, in that case we should get a 0 value at theta equal to 0 and phi is equal to 0, right? So we should get 0 value. But where 0 value means this is the numerical value of 0, means minus infinity dB, right? So ideally we should get minus infinity dB, but any value which is better than which is less than 30 dB, we can assume that is a good value, right? So we, in our case, we are getting a null depth of minus 35 dB, better than 35 dB. If you see here, at 0, if the target is right at the center, we are getting better than 35 dB. Here also we are getting minus better than 35 dB. So the null depth of this is very good, and this null depth actually depends on the monopulse comparator accuracy, how accurately the monopulse comparator is calculating the difference, and the second factor is how the antennas are similar in characteristics or not. So there are two things. One is the monopulse comparator. Monopulse comparator must calculate the difference perfectly. The accuracy of the difference calculation in the monopulse comparator should be very good. And the second thing is the antenna should be similar. If the antennas are not similar, then also null depth will be poorer. And if monopulse comparator is itself is not calculating the difference accurately, then will also affect the null depth. We will get a poor null depth in that case also. So these are the two things we have to see in the sum radiation pattern and the difference radiation pattern. This is just the comparison of our work with the reported work. And if you see few of the papers, the first one is multi-layer based, similar to our paper, but in that case they are using a comparator design using a magic T, a planar magic T. And in our case, we are using a rat race monopulse comparator. In our case, we are getting a good null depth and high efficiency. Efficiency of our is approximately 68.9%. In the first paper, it was not given actually, but the main thing was they were using magic T as a comparator, which was making the structure complex in design. Right. The second paper was working at KU band, and there they were the area was very large, but this was a single layer only, the single layer, and they were using branch line couplers as a monopulse comparator. The disadvantage was a low efficiency of that antenna. The third paper was getting efficiency of 32% with the narrow bandwidth. The bandwidth was limited because one thing is they are using single layer, and the second thing is they were using branch line coupler. In our case, we are getting more bandwidth, good null depth, and good efficiency also. So this is all about the monopulse antenna. Let me conclude my presentation. Starting from the concept of monopulse tracking for radar applications, we discussed the broadband EMCP microstrip antenna arrays, and then we discussed the different configuration of monopulse comparator, which were integrated. So we integrated these two to form a monopulse antenna, and we discussed about the null depth, and we have seen very good null depth and isolation between the ports have been obtained from our design, along with a good efficiency. So this is all about my presentation. These are some of the publications that you can see, and if you have any doubts, you can ask now. Hello.
So participants, now you can ask question to speaker, or you can type if you are not able to speak. We are expecting one question from each participant. So kindly ask questions.
Sir, can diagonal difference port? What is the question? Dr. Singh, can you please read the question for me? I'm not able to see the
Yes,
question.
yes, yes. One person, Suraj Sharma, is asking, sir, can diagonal difference port info be useful for any application?
Yes. It's a very good question. Actually, there are two papers. Till now, I have seen only two papers which are discussing about this diagonal difference. The diagonal difference is actually sometimes when we design and we are not getting the perfect difference, then the diagonal difference port can be used to match that particular difference. Means you can improve the accuracy of your difference ports by changing the load impedance at the diagonal port. So instead of using 50 ohm, if you use some other value of the impedance, then what will happen? The reflection will occur, and those reflections actually undesired for our design, but these undesired values can be used in improving the accuracy also, if somehow after fabrication we are not getting the accurate results. So this diagonal difference can be used for improving the accuracy actually. There are two papers on this where they have discussed about the diagonal difference. They mentioned this diagonal difference. They have, I think, mathematically also proved that the diagonal difference can be used to improve the results of in case after fabrication we are not getting the accurate results, then diagonal difference can be used to improve the results. So sometimes undesired things can be used in our favor also. So in this case, actually, the diagonal difference is not useful as of now, but it can be used when we are not when the situations are not in our favor. Then we can use the diagonal port to make the situation in our favor actually. So there is no need to design the monopulse comparator again. Even if you are not getting the accurate difference, you can use the diagonal port for improving the accuracy of the difference port.
Okay, so next question is from Miss Sharifa. She's asking, is horn-shaped microstrip antenna or double-ridge horn-shaped antenna better for biomedical related projects?
Um, this is a very general question. Means
Yes.
uh, uh, See I don't know for what in biomedical application you how much bandwidth you need. So based on the bandwidth or the gain requirement, as I discussed, the few of the parameters. If you see, I have discussed the parameters here: frequency of operation, bandwidth, side lobe level, physical size and weight, power handling capacity, gain, beam width, polarization. So these factors you have to choose accordingly. Means if you see, if you are working at millimeter wave frequency and you want to mount your antenna on such a platform where high heavy weight is not possible, it will not be able to handle the heavy weight. So then you have to use and you also want to use the horn antenna. In that case, you can go for a SIW horn antenna, or in case the you don't have any physical size constraints, then you can use a 3D horn antenna also. So it all depends on the application and the platforms and the functions for which you are designing your antenna. So for biomedical application, if you can tell me how much bandwidth and what are the constraints where you are going to keep it like that. So based on that, actually you can choose which antenna. So I can just tell you about this like that.
Any other question from any participant?
Hello, sir. Hemant, sir. Good
Yes.
evening, sir.
Good evening, sir.
Yes, sir. My doubt in array feeding technique. You are
Yes, sir. Yes,
using
sir.
some power divider. Can I?
Yes, sir. Yes, sure,
Uh,
sure, sure. Let me show. Yeah, this one,
yes,
right?
sir. In generally in Wilkinson power divider case, what they are using to match the output ports, they are using some isolation resistors.
Right.
Yes, sir. Here you didn't use any resistors. How you match that output ports in your case?
Yes. Actually, sir, Wilkinson power divider is used here. We generally use a resistor if we want to use the power divider as a combiner also, right? If we don't
Okay.
want to use that combiner, then there is no need of using this, right? So we are not going to use this as a power combiner. So there is no need of using this resistor. So Wilkinson power divider is basically making the structure reciprocal. Basically, if you
Ah,
give the input here power P, and you will get here P1 and P2, which P1 plus P2 will be equal to P, right? And if
yes,
you
sir.
give the input here at P1, here you will get give the input at P2, you will get here P, which will be equal to P1 plus P2. So it will work as a power divider as well as a combiner. So in
Come.
Wilkinson power divider, we are using that resistor only so that we can use that power divider as a combiner also. But here there is no need to be using as it as a power combiner. We only going to divide the power. We are not going to combine the power. So power is not we are combining here, right? So there is no need as such in this case.
Okay, sir. Okay, sir. Thank you, sir.
Okay.
Okay, so one more question from Suraj Sharma. Why do we prefer circular shaped geometry? And another question is, if possible, then can you please give reference of diagonal difference papers?
As of now, a diagonal difference paper. Let me. Yeah, I'll send you. I'll send the diagonal difference reference to Dr. Singh. I think he can share with the participants.
Yes,
I'll
that would
share.
be great.
And
Yeah, I will.
and if you want to check yourself, then you can go to this paper. You can just check. Let me show you. Yeah, you can check one of my paper, Monopulse comparator. It is published in IEEE Microwave magazine. So if you see this paper, the paper number 3, in this I have given the reference to the diagonal difference. You can check the references of this paper. This is given in this paper. So references, you can see the diagonal difference. Two papers are there. I'm not sure which number is there, but if you see all the references, two references are based on that diagonal difference. So you can refer to this paper. Right. monopulse comparator, which is published in IEEE Micro magazine and in 2019. And the answer to your question that why the geometry should be circular. Actually, circular geometry is generally preferred compared to the rectangular. Depending, again, it depends on the platform where you are using the the size constraint they have given because they wanted to put in on the aircraft. So if you have as such circular have other advantages also means compared to the rectangular, it will give you less side lobe level compared to the rectangular, as I discussed, the tapered geometry and the uniform geometry. Uniform distribution will give you more side lobe level, tapered one will give you less side lobe level. So basically the circular geometry will also give you a better in terms of side lobe level also. And second thing is depends on the platform, depends on the physical constraints that they have given to you, right? So based on that you have to design. So they were this requirement was to put it on a platform where the circular geometry was preferred. So that's why we designed like that.
Okay, I will call the name of participants. Mr. Akshay Jain, do you have any question to participant? Are you here, Mr. Akshay Jain? Okay. Next participant, Bhimrao Jadhav. Do you have any question?
No, sir, from my side.
Okay. How do you like the presentation or the topic? Is it new for you or it is means you know about this topic or you are working on such kind of things?
Actually, I am working on a microstrip antenna.
Okay.
I know little bit about power divider, Wilkinson power divider. Comparator is new for me.
Mhm.
The corporated feed and series feed is I have gone through some simulation like array of antenna.
Mhm. Okay. Okay.
Comparator and these things is new for me.
Okay. So you are working on this with software, HFSS or CST?
CST.
Okay. So when you will join this offline FDP, then we will have the hands-on with the CST. So you will get more means not only antenna, we will have these power dividers and all these things in a
Okay, sir.
hands-on session.
Okay, sir. Thank
Yeah.
you.
Okay, thank you. Dr. Makran Jadhav, are you here? Do you want to say something? Mr. Makran Jadhav? Okay, Dr. Hemlata Jadhav, do you have any question?
No, sir, no question, but the session was really informative. Many of the things were new to me actually.
Okay.
Yeah, but it was very, really nice session, very informative. Definitely it will be helpful to me. Yeah, thank
Okay,
you.
okay, ma'am. So you are working on antennas?
Actually, one of my groups, sir.
Okay, okay,
Yeah, yeah.
okay, fine. Thank you. Dr. Pranita, do you want to say something? Next, Mr. Ganesh Gaikwad. So do you want to say something?
Sir, basically, electromagnetic coupling practically is a new concept. Actually, we have not applied that.
Okay, sir. Okay. So you may be knowing that direct coupling, which is a
Yeah,
conventional microstrip
direct,
patch.
contact type and all those kind
Yeah.
of.
Okay.
There
So
are
are
many
you
things in
working?
that, but
Are you working on such things, sir?
Yeah, in past I have worked in this all method microstrip pack antenna, then in bandwidth enhancement techniques of pack antenna, then EVG, all these techniques I have worked.
Oh, okay. So yeah, kindly you can also suggest some students to work on these topics because these are actually new things, so that student can get means more ideas related to these topics. Or you can maybe contact to the person who already mentioned the email ID. If you have any query, maybe later your student may have any query, they can directly ask to the speaker.
Okay, sir.
Okay, thank you. Next, Jagtap Suraj Sunil Kumar, are you here? Do you want to say something?
Sir, session was a very informative session, sir. And no questions, sir.
Okay, so are you working on these antennas kind of
Yes,
topic?
sir. Currently working on microstrip antennas, sir.
Okay, so which kind of feed you are using?
Sir, I am using CST software, sir.
Okay, fine. Thank you. And next, Prashant Dahale. Sir, do you have any question?
No, sir, because I'm new to this concept. I'm trying to
Okay,
get
sir.
as much knowledge I can get from this workshop.
Okay, sir. Perfect. Yeah, nice.
Thank you.
Then Mr. Samadhan Mali. Sir, do you have any question? Okay, we can go to next participant, Satish Kannan. Do you have any question? I think you have asked one question, or maybe you may be having other question you can ask.
No, sir, no other questions. It's okay.
Okay, so you are working on these kind of topics?
Yes, sir. I'm working on variable antenna, and then now I'm designing some power divider. In that one, I have doubt. I have barely.
Okay, fine. Okay, fine.
Okay.
Thank you.
Okay, sir. Thank you, sir.
Next is Mrs. Sharifa. Do you have any question? Okay, next, Mrs. Sheetal Atole. Ma'am, do you have any question related to this topic?
No, sir, I don't have any questions, sir.
Okay, so are
Okay,
you working on these kind of topics?
No, sir, actually, I'm working on radar only, not on
Mhm.
antenna.
Okay, but in radar, maybe you may be working on signal processing side or maybe different.
Yes, sir, latter maybe it will be working on signal processing. Latter, not now, sir.
Okay, because
Okay.
in radar also antennas are used. So
Yes, sir, yes, sir.
this concept
But
is actually this antenna is
but
application for radar only, tracking
yes,
targets.
yes, sir, but I'm working only on parameters right now.
Okay, fine.
Okay, sir, thank you.
Okay, thank you. Next, Suchita, ma'am, do you have any question?
Sir, I don't have any question, but the session was too good, sir. I like it.
Okay, ma'am. Okay. Thank you. Next, Suraj Sharma. Do you want to say something?
Yes, sir. I want to ask one more question, sir. Actually, sir,
Okay,
I am not well, sir. That's why I was typing.
Oh, okay, no problem. You can type. I can read.
Okay. Yes, sir. I will ask you, sir, now.
Okay,
The
fine.
question is, sir, this currently we are adding RMSA. So can we use it for millimeter frequency? Replace that antenna with a millimeter antenna. So will this overall configuration will work or not, sir?
So for
Yes.
millimeter wave,
Yes.
yes, means we actually I actually designed one monopulse antenna for Ka-band application also. If you see, if you want more detail, you can check one of my paper. Let me show you that paper. But there, what we have used instead of microstrip, we have used a slotted waveguide fed microstrip antenna array. So if you see this patent is also filed on that slotted waveguide fed microstrip antenna array. This was designed at Ka band, so millimeter wave frequency, approximately more than 35, around 35 gigahertz. So you can see the paper, this paper, and one paper is on this. Let me show you the conference paper also. Uh, the comparator part that I have shown you, waveguide monopulse comparator, right? So that in that case we have used waveguide comparator, waveguide magic T as a comparator, and the antenna part that we have used is we have used waveguide, and in that we have cut some slots, and those slots based on the slots we have put a microstrip patch to excite. So excitation of the microstrip antenna is done using the waveguide slots, right? So that's why the name of that antenna is given as a slotted waveguide fed microstrip antenna array. So in millimeter wave frequency also we can design. You can check the more details or the paper published on this waveguide fed microstrip antenna array, and the paper, that conference paper that I discussed, the compact waveguide monopulse comparator at Ka band for monopulse tracking. So more details you can see in these papers. So this slide, I think sir will share with the participants. I have already forwarded the slides to the Dr. Singh, so he will be sharing based on the after the presentation. You can check these references.
Okay, sir. Can I communicate with you, sir, on this if I have any clarification?
Yes, you can communicate to me. The emails are mentioned here. You can send your query anytime to these emails. I will reply at the earliest.
Okay, thank you, sir. Thank you, sir.
Thank you.
Okay, thank you, Suraj. Now we will move to next participant, Suvarna. Ma'am, do you have any question?
Good evening, sir.
Good evening, ma'am.
Yeah, thank you. Sir, the session was really nice, and I just want to ask, maybe that question is a very basic, but as I'm working in the signal system on package, I want to ask what are other substrates on which we can implement this kind of antennas, and which parameters. Actually, I do understand that dielectric constant and loss tangents are very important parameters, but other than this, which parameters we have to concentrate if we are going for this kind of designs?
The substrates are actually main. Generally, we use RT toroid substrate. If we are working beyond, you can say 7 to 8 gigahertz. So generally, up to 3 gigahertz, we recommend we can use FR4 substrate. Again, it depends on the application. So if you are designing the antenna for commercial application, for the commercial application, generally we use FR4 substrate, and that work is only up to 3 gigahertz. But if we are working at very high frequency and for satellite applications or space applications or defense applications, so accuracy is more important than the cost. Then we use generally less lossy substrate. There are other substrates available like there are like apart from this 5880, we have a 5870 also, and there are 2-3 more substrates. Arlon is there. Arlon is also one of the substrate. There is Arlon dielectric constant is also less. But the main thing is, if you want less dielectric losses, the loss tangent should be as low as possible. As low as possible. The loss tangent should be less. But for getting a loss tangent less, you have to pay more money for that, getting the substrate. So substrate will be
So
costlier.
is this the best substrate we are using for such applications?
Yes.
Whatever you have
For
mentioned right now.
so the nowadays, if you see for these applications up to means in the X band or Ka band, we generally use RT duroid substrate is the best substrate that we use. It's a loss
Thank
tangent
you
is
so much.
very less, very less loss tangent, 0.001. So it is very less lossy substrate, but the cost is very high compared to the lossy substrates like FR4. FR4 substrate is very less loss, very less, very cheaper substrate compared to RT Duroid. And even RT Duroid substrate, you won't get it in India. You have to import it from US actually. Yes. So main
Okay,
thing
sir. Thank
while
you.
deciding the substrate is you have to check your frequency, at which frequency you are working, and you have to check for what applications you are designing, whether it is for commercial application or for defense or space or satellite applications. For them, you have to have a good accuracy. For accuracy point of view, you have to get a good substrate, less lossy substrate. And for commercial application, these things won't matter. So you can use FR4 substrate as well for commercial application.
Okay, sir. Thank you. Thank you very much, sir. Thank you.
Okay, thank you, ma'am. Next participant, Swapnil. Okay. Sir, do you have any question?
No, sir, no. Actually, I'm new to this topic, so yeah.
Okay, sir. Okay, no problem. Fine. Thank you. Next participant is Swati. Ma'am, do you have any question?
Hello.
Hello. Yes, ma'am.
Yes, sir. Sir, actually, I'm working on MIMO antenna. Sir, my question is how I can improve the bandwidth of the MIMO antenna.
Bandwidth of the MIMO antenna. So means which antenna you are using? Element is you are using for your MIMO application?
So, what? Pardon? Substrate.
Means which element you are using for MIMO application?
Which type of radiator you are using? Monopole
Using
antenna or some any other your ultra wideband antenna or other?
Ultra wideband.
No, means I mean to say you are using monopole antenna, dipole, Yagi, Uta, LPDA. Which antenna you are using
Sir,
as of
patch. Actually, I
microstrip
have
patch
started
antenna?
patch. Yeah.
Okay. So actually, for increasing the bandwidth as such in MIMO, I'm not able. I won't be commenting. But for increasing the bandwidth of the patch antenna, there are so many techniques available in the book Broadband Microstrip Antenna by Professor Girish Kumar or Professor KP Ray. In that book, you will get so many techniques are there to increase the bandwidth you can use. So in my presentation, I used EMCP, but there are other techniques, gap coupled, inverted inverted EMCP, and direct coupled, and there are, I think, so many techniques. If you see in that book, there are 2 or 3 chapters are totally based on techniques for increasing the bandwidth. So
Okay.
you can check that book for for increasing the bandwidth of your patch.
Okay. Sure, sir. Thank you, sir.
I will add one more thing here. If you are using this MIMO antenna for maybe broadband, like UWB band or maybe more than 4 or 5 gigahertz band, then you can use monopole kind of antenna, printed
Sir,
monopole antenna.
I am designing antenna for millimeter frequency range.
Millimeter wave frequency.
Yeah.
Okay. So what exactly frequency range? Around 60 gigahertz or maybe
Sir,
less?
it is between 24 to 40 gigahertz.
24 to 40. Okay, so it is not a small band. It is actually a wide band. So
Yes.
you can choose this uh, monopole kind of antenna.
Okay.
Otherwise, if you use patch antenna, then you have to do more with that to get that much bandwidth.
Yeah,
Okay.
right.
As sir told in his presentation that we can increase the bandwidth, but again we have some limitation and what kind of radiation pattern we need.
Right.
That your radiator can give that kind of radiation pattern what you want. Then you can choose the shape of radiator on that basis.
Okay.
Yeah.
Okay, sir.
Okay.
Thank you.
Thank you. Next, Triveni. Ma'am, do you have any question?
No, sir.
Okay. Thank you. Next is Vidya. I think she wrote something. I will. Very informative session. Thank you, sir. Okay, ma'am. Thank you. And the last participant is Yugandhar Chincholkar. Sir, do you have any question?
No, sir. I am recalling that content, whatever we have learned in previous year. So presently, I don't have any question about that.
Okay, sir. No problem. Fine, sir. Okay, so if no participant have any question, then I think we can close the session. So we were grateful for, Dr. Kumar. We were grateful for your presence among us today. You have
Thank you, Dr. Singh.
discussed so many, I would say that a very interesting presentation. It is actually a very different topic. It is not usual one. So maybe participants will take, or also for me, I learned so many things from this. So
Thank you,
thank you very
Dr.
much.
Singh.
And I again thank you for accepting our invitation and give a talk on this important topic.
Thank you. It is my pleasure, sir. You have invited me, and I got a chance to show my work to the audience online in this virtual platform. Thank you. Thank you so much, Dr. Singh.
Yeah, so thank you very much, and thank you participants for joining the session. So now we can close. Good evening to all of you.
Thank you.
Can leave.
Thank you all.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir. Thank you.